So this video is just going to give you a quick sense of how absorbance gets measured in terms of the hardware. Um, Most of this is relegated for an instrumental course, but the last week of any analytical course is typically an intro to an instrumental course. So give you a little bit of sense so you understand practically how this might work. So when you're measuring absorbance, you saw what a general spectrophotometer layout might look like in a really simplistic version of that, at least. One of the key elements there is what you put your sample in, and you're used to using, at least most of you have probably used a cuvette before, and the standard cuvette is one that looks like this, where you've got a 1.000 centimeter path that's precision machined. If you remember back from Chem 107 and Chem 108, you may have used the ones that were rounded that looked like test tubes. Those are much, much worse in terms of error because as you have incident photons on a rounded object, there's a much higher proportion of those photons that are going to be refracted because the thickness, at least the apparent thickness of a curved surface changes depending on where the photon strikes it. So the best, at least in terms of minimizing error, types of cuvettes are those that have these really, really flat sides. And ideally, the two sides, the two opposing sides, are precision machined in terms of flatness, and they're super, super parallel to make sure that you don't have one side that enters completely orthogonal and then the other side that's 1 or 2 degrees off, which again is going to change the thickness of that depending on what orientation you have this thing. So in terms of minimizing error, it's really important that you have a really good cuvette if you want to get the really reproducible and accurate numbers. Of course, you don't always have, if this is 1 centimeter by 1 centimeter and then it's maybe 4 or 5 centimeters tall, then we're talking about several milliliters to fill this thing up. You might not always have that, especially if you're working in biochem or you're working with things that are you just don't have much of it around, in which case you can have cells that are like this, where you have still the same format of a 1 by 1 that fits into most sample holders and most spectrophotometers, but you can see that the volume is taken away by inserting more glass. We call these things microcells. In that case, there's only one direction that the light can pass through. Of course, you don't want it to pass through this way because it's passing mostly through glass. You're going to pass it through that way instead. In terms of the region of the EM spectrum that you're going to measure absorbance, I mentioned or I alluded to before, if you're measuring visible light, then you can get away with acrylic or glass. If you're measuring UV, then you need quartz, which makes it much more expensive. Quartz takes several thousand degrees to blow it. Because it's crystalline and non amorphous, rather than like soft glass, which may take 600 C to blow it. And so it's industrially a much more challenging manufacturing process. We can also have these sort of cylindrical cells where there's larger sample volume or you need them to be closed. There's various reasons why you would want these. Maybe you purge these with gas because you have an oxygen sensitive species in here. Or you can have these as flow cells, so you connect a tube on one side and a tube on the other, and so maybe you're doing some time-dependent reaction and you want to do this in a flow type geometry, or you're purging, or there's a million different reasons experimentally why you might want to do this, but notice that the ends of this are flat. And oftentimes you'll end up having actually just a tube that's been cut off with a glass saw and then glued on the end are quartz windows, so that you have soft glass here, which is cheap and easy to blow, and then on the end you have these discs of quartz. We have all these types of cells in the department because we all use them for different reasons. You can see that the path length, of course, in Beer's law is linear with absorbance, and so in certain cases you may be measuring really small concentrations of stuff, in which case the absorbance may be sort of non-detectable above the blank. And one sort of simple fix for that is just to crank up the path length. I'm not showing you here. Let me show you one, maybe. So I've got one down in the bottom left here. This is what we call a multipath cell or a long path length cell. And the idea is here you have the entrance on the left, and then you have your exit over here, and usually this is a long tube, and then the tube is coated with a reflective coating, usually silver metal like a mirror, or chromium or some highly specular reflective surface. This stuff enters at different angles, and we can control that angle, and what it does is it bounces off inside of the cell and maybe even back and forth, and oftentimes you can get maybe 100 or even 1,000 passes inside the cell from a single photon before it finds the exit slit over here, which means maybe this whole thing is a few centimeters long, but the path length of the photon then artificially gets increased to several meters or hundreds of meters, in which case you are cranking up your absorbance sort of artificially. This is a nice trick, especially for gases. You'll mostly see these for gas cells. So if you want to measure like carbon monoxide in air, one way to do that is to look at its vibrational spectrum using IR absorbance. The molar absorptivity in the infrared of gases is fairly small, which means that this epsilon is small. So you got a small epsilon, and the concentration of carbon monoxide or CO2 in air is usually in the part per million range. So one good way to crank up the absorbance into a measurable range is to use these multipath cells. So another thing in terms of infrared that we have to consider is that infrared is essentially heat, at least how we perceive it, which is absorbed by glass. So we can't use any of this stuff. None of these cells work for infrared. And many of you probably used an FTIR for organic, but you never really even thought about this step. So I'll give you the two different general ways to do this. The first way, and the old school way, this is the way that I learned, is that infrared light is not absorbed by ionic salts, things like KBr, sodium chloride, which is interesting in and of itself from a material science perspective. But for that reason, salts are essentially the glass of the infrared region of the spectrum. And so what we do, and we have this capacity at CC, is we can take a little vise and then pour a little bit of clean KBr powder into it, and then we crank it down, and what will happen is if we put enough pressure, we'll actually force all of the ionic bonds to align in a certain way, and we do this process called vitrifying the salt. Vitrifying, it comes from the word of glass or transparent, and so we end up making what looks like a glass window, but it's actually made of a salt. And then what you can do is take, say you synthesize a compound, take a drop with a Pasteur pipette out of your round bottom, and then you put one drop on the surface of that salt glass, and then you put that in the path of the infrared beam, because we know that the salt itself isn't going to absorb any of that infrared radiation. Because salts are hydrous, you never want to do this. That's why it says never do this. You never want to touch the place, because you're not only are you going to probably cloud up the window because of the moisture in your fingers, but also your fingers are dirty. And so you're going to see all the oils and all the junk that you've touched recently. The other way is to use this method, and this is the way that you used, which you didn't even know, but it's this amazing technology. So you use this tool, the FTIR that we have two of them. We have a research grade one for gas type measurements, which you did not use, and then we have more of a routine small benchtop one that we use for orgo, just because it's, you don't need to be precise or accurate in organic chemistry at all. And so you were mostly looking to see, did that transformation occur? Looking for broad functional groups, but you were not quantifying on this tool. And for that reason, you were using this thing that had another hyphenation here. We call an ATR FTIR, and what that stands for is attenuated total reflectance Fourier transform infrared spectroscopy. The ATR is the sample introduction step. So instead of using this, what you did was take a small drop and you put it on the surface of a little window. And what happened there is you've got all your molecules. This is sort of a zoom in of that window. you put your drop, and so your molecules evaporated from the solvent, and you end up having a thin layer on the surface. So then the infrared light comes in at a particular angle. If you remember back from your physics course, depending on the difference in refractive index between two different materials that are in contact with each other, and depending on the angle here, the incident angle, we can actually get what's called total internal reflection, TIR. Total internal reflection means that the vast majority or percentage of the light actually is not going to pass through and transmit as long as this angle and the difference in refractive index are correctly chosen. And so it tends to bounce back, and then it continues to bounce through here. Every time it comes up to this interface, it propagates this thing called an evanescent wave. And so there's this standing sine wave from the infrared light that reaches up just far enough to sample our sample that's stuck to the surface. And every time that wave, that standing wave, samples it, it can be absorbed if it's of the right frequency. In terms of its quantization. And so this is sort of like a long path length here because it's sampling multiple times. And so by the time it exits, you end up having a much higher absorbance than you would have if you only had a single path length. And the cool part is it didn't require you any sample prep at all. You just literally took a drop straight out of your round bottom, put it on the surface, and then you run this really fascinating reaction. Of course, this crystal, the crystal we use is made of diamond, synthetic diamond. Typically the materials here to get this to work are pretty expensive, but they last for a long time as long as you treat them right. And so this was the tool that you used, which was the attenuated total reflectance adapter to a standard Fourier transform infrared absorbance cell. So I'll just mention briefly for your own understanding, because these are super powerful techniques. So far what we've essentially measured is the absorbance and transmittance of light, but we can also measure the reflectance of light, which in actuality all of the light has to come from the absorbance, the transmittance, and the reflectance, but we often don't think about that component. We often just think about the absorbance and the transmittance components because they're pretty intuitive. But often you have opaque samples, things that don't absorb, or they're too thick or too opaque to actually transmit or absorb, and so the only option there is to shine light and reflect it off. And there's two different types of reflection. We can either have specular meaning like mirrored, so you get just whatever comes in, that incidence angle is the same as what goes out, that exit angle. And we can measure reflectance like that, or we can measure it from really rough surfaces called diffuse reflectance. The way that diffuse reflectance works uses this thing here called an integration sphere. We have one of these. They're really common. So the whole object is essentially this opaque thing that's rough. You put your sample in on the other side here. Your incident light comes in through a tiny pinhole over here, and then it reflects off of your sample, and then it can bounce around this sphere. And then eventually that light will reflect back up to where the detector is as it bounces around enough, and so we're collecting all of that light. That's really what the integration sphere is. There's some tricks that you need to do to get a reference beam to understand like what your I naught is versus your I. In this case it would be R naught versus your R. So you have to play some tricks to do that, but generally you're collecting all the light. That's how you would measure the diffuse reflectance. This is super common. I did this a lot in grad school because a lot of times I'll synthesize like a powder for a new material that we're using in like a photovoltaic, and I want to characterize its infrared absorption, and the only way to do that would be to conduct a diffuse reflectance measurement like this.